We have a function here being defined by an infinite series. And this infinite series, if we look with a little closer inspection, it's clearly a power series. Each term is a power of x being multiplied by some coefficient. So this, for example, is 2 times x to the 0. That's just 2. And it looks like it might be a geometric series. But in order to test that, we have to make sure that there's a common ratio, that to go from one term to the next, we're multiplying by the same amount. So go from 2 to negative 8x squared, what do we have to multiply by? We'll go from 2 to negative 8, you have to multiply by negative 4, and then there's no x squared here, and now there is, so we multiplied by negative 4x squared. Well, to go from negative 8x squared to positive 32x to the fourth, once again, we multiplied by negative 4x squared. So each time we're multiplying by negative 4x squared. We do it again right over here. So it looks pretty clear that our common ratio is negative 4x squared. Now what's neat about this is that we can then use this information. We know how to take the sum of a geometric series, of an infinite geometric series, that when we know its common ratio. We've proven this in previous videos, but the formula is essentially, it's the first term right over here. It's going to be 2 over 1 minus the common ratio. Well, what's the common ratio? It's negative 4x squared. Negative 4x squared. So if we want to simplify this, this would be 2 over 1 plus 4x squared. So this is just neat from a mathematical point of view. We took this infinite series, this geometric series, which is a special case of a power series, and using that, and using what we know about the sums of infinite geometric series, we were able to express this in a more traditional form. Now, as always, you're probably thinking, well, why was this useful? Well, oftentimes in mathematics, you'll actually have functions that look maybe something like this, and they're hard to kind of deal with in your head. And if you say, well, as x changes, what happens to the value of the function? Or as the value of the function changes, what must have happened to x? But if you can approximate this with a few terms of the power series, then this might be an easier way to at least approximate what's happening. And this is done in engineering, and this is done in finance, and it's just interesting in general.